Welcome to CET2112C, which is Digital Systems 1. My name is Professor Evans, and in this video, we're going to be discussing number systems. So the purposes of this video are that you will be able to define what a digital signal is. We're also going to learn how to convert from one number system, such as the decimal, binary, hex, octal, or BCD number systems, to another number system. So within all of these systems, we're going to learn how to convert from one to another. And then we're also going to discuss the idea of parity and determine how a proper parity bit would be provided for a given transmission system. So first, I'm just going to begin with a quick introduction to the topic of digital systems in general. If this is the first course you've ever taken in digital systems, this is going to be a foundational course that helps you to understand and relate to all of the digital devices that are around you. If you stop for a minute and try to think about all the digital devices you've used just today, your list would probably be pretty long. Think about all of the electronics that we use, all of the sensors that we use to control the temperature in our homes or to control our cars when we drive, all of the electronic appliances in our homes. Of course, all the digital gadgets that we use today. We can very clearly see that digital devices are everywhere. And the purpose of this class is to start understanding on a very, very basic and fundamental level how these digital devices work. So let's begin with a basic definition. Digital systems are systems that deal with things that are in one of two distinct states. Those two states are commonly referred to as 0 and 1. Or we say high and low, or we might say on and off, or we might say open and closed. At the end of the day, there are two possible outcomes, and our system, a digital system, is going to be a system that is only ever in one of those two states. Either it's on or it's off. Either it's high or it's low. Either it's 0 or it's 1. There isn't a partially high, partially low, negative on, 0.5 off. There is no in between. It's black and white. Either it's 0 and 1, high or low, on or off, open or closed. That's our basic definition of what a digital system is. So for any given digital circuit, the output is only ever going to be considered high or low. That's it. There's no in between. There are no alternatives. That's our definition of a digital system. On the screen is an example of a digital circuit. If you don't know what these symbols mean, you will know what they mean in a few weeks. Each one of these symbols represents a logic gate. You'll see on the left, these are the inputs to the circuit, and they're just labeled with variable names, A, B, and C. Those are inputs. And then we have an output on the right called Q. Since this is a digital system, this is a digital circuit, so the inputs, A, B, and C, can only ever be represented by a 0 or a 1, a high or a low, on or off. Now, in the real world, the concept of a 0 or a low is representative of a voltage measurement that's typically 0 to 0.8 volts. When we say that something is high, or that it's on, or that it's a 1, that's representative of a real-world voltage measurement of around 5 volts. So that's how we translate the idea of 0 and 1 to an actual voltage measurement that you would see within a bench. Whenever we build a digital circuit, if we were to take an oscilloscope and generate a waveform for the output of the circuit, it might look something like this. Notice that within the output of this circuit, the output is only ever at a high state, like this, or a low state, like this. There's no other alternatives, there's no in between. So again, here are those names for the high state. So the output would be considered high, or 1, or closed, or on. Those are all interchangeable terms for the high state of a digital system. And then the low state is also called 0, open, or off. So within the context of a digital circuit, your inputs and your outputs will only have either a value of high or low. That's it. There's no in between. Analog circuits are circuits that you may have dealt with if you've taken, for example, a fundamentals of DC class or a fundamentals of AC class. DC and AC circuits are analog circuits. That means that for a given input, you could have any number of outputs. Analog circuits are things like maybe the odometer in your car. As you press the gas pedal down, you could have a wide range of outputs representing your speed. A thermometer is another example of an analog measurement indicator. As your body temperature changes, or as the temperature of a liquid or the air changes, you have a number of possible values that temperature could be. That's analog representation. Digital representation is considered a non-continuous quantity, which means that you only really have two possible outcomes shown on the graph below. Either it's high or it's low. That's it. This analog graph shows that for any particular value of x, you could have a number of different values for y. Let's say that I pick a value of x to be right here along the x-axis. Y might be a very high positive number. If I were to look at the corresponding value of y when x is maybe right here, we'd have a negative number. As you travel along this wave, you would have a number of different values for y depending on what x is. But if I look at the same graph, at any point in time, if I look at a value for y, by going along the x-axis, x could be here, or here, or here, or here. It doesn't really matter. As I travel along the x-axis, y can only ever be 0 or 1. There are no other options. That's the definition of a digital circuit. So the first step to understanding digital systems and digital circuits is to understand number systems. So the purpose of this video is really to help you understand the binary number system. That's the language that computers speak. It's fundamental to any field related to digital systems and microprocessors. Also computer programming. So if you've ever seen any reference on social media or seen jokes about computers talking in ones and zeros, that's the binary number system. And today we're going to learn what that binary number system represents and how to convert from binary to decimal and to some other systems. So in our daily lives, we use the decimal system. That's what we've grown up using. It's a base 10 system that contains 10 digits. So our normal system contains digits 0 to 9, and we base all of our numbers from that system. The binary system is a base 2 system. So instead of having 10 digits, it only has 2 digits, and those 2 digits are considered to be 0 and 1. So to learn how to convert from a binary number to a decimal number, we're going to go all the way back to 3rd or 4th grade when you learned about the place value system. Let's take the number 5,432, for example. We can break that down into a ones place, a tens place, a hundreds place, and a thousands place. We know that the ones place begins on the right, and as we go to the left, each place increases by a factor of 10. We know that the ones place is the place that represents how many ones we have. So if I have 2 in the ones place, that means I have 2 ones, or 2 times 1. If I have a 3 in the tens place, that means I have 3 tens, or 3 times 10. If I have a 4 in the hundreds place, that means I have 4 hundreds. And if I have a 5 in the thousands place, that means I have 5 thousands. This right here is what you learned when you were probably in elementary school when it came to classifying numbers. So let's take each one of these place values a step further. I'm going to replace each digit in the place value with an exponent of 10. So instead of saying 2 times 1, I'm going to say 2 times 10 to the 0 power, because 10 to the 0 power is 1. Instead of saying 3 times 10, I'm going to say 3 times 10 to the first power. Instead of saying 4 times 100, I'm going to say 4 times 10 to the second power, and so on. And now we have a pattern. When we look at our place values, starting from the right and working our way to the left, we can see that each place is simply an exponent of 10, beginning with 10 to the 0 and increasing by 1 as we move to the left. This is the place value system, and this is how we classify the number 5,432 by breaking it down into place values. We're going to do the same thing with the binary number system. The most important thing we have to realize here is that our place value is determined by the base of our number system. 5,432 is a base 10 number. That's why we multiply in each place value with an exponent of 10. That 10 comes from the fact that the number I began with was a base 10 number. So we're going to take this concept and extend it to a base 2 number. So here's a reminder of what we just went over. Our number, 5,432 in the decimal system. And now we're going to look at a binary number. The number we're going to look at is called 1011. The first thing I want you to notice is that there's a subscript at the end of each number. That's because we're now dealing with different number systems. We have to make a difference between a base 10 number and a base 2 number. If not, I could read this number right here as 1011, but that's not what this number is. This number is the number 1011 in binary, and that's how we would read it out loud. There is no thousands place in a base 2 number system. So we would not read this as 1011. We would read it as 1011. And I would know to read it that way because of the subscript that is provided. So for this class, for the entire semester, anytime you write a number, you are always going to include a subscript because we need to know what number system we're referring to whenever we write these numbers. So you'll see that there's a 10 as a subscript here, indicating that 5,432 is a base 10 number, and that's a decimal number. So now I want you to take a look on the right side of the screen at the number 1011. Again, that's a base 2 number, that's a binary number, and we're going to create place values based on the fact that it's a base 2 number. Notice that for each place value, we're going to write the base. See how this is always the same? It's a 2. That 2 comes from the fact that I'm starting with a base 2 number. Then for each place value, I'm simply going to have exponents of 2 instead of exponents of 10. So with the number 1011, my place values begin at the right, extend to the left, and they begin with 2 to the 0, 2 to the first, 2 squared, 2 to the third power. Then we simply take each number on top and multiply by that place value. So in this place value, we have 1 times 2 to the 0 power. This place value, we have 1 times 2 to the first power. This place value, we have a 0 times 2 to the second power. And for this place value, we have a 1 times 2 to the third power. Now you're simply going to simplify each one of those and add them together. Once you simplify each one of these, we'd have 1 times 8, 0 times 4, 1 times 2, and 1 times 1. We're going to take those and add them together. Once we do, we'll get the value 11. The value 11 is the decimal equivalent for this binary number. So 1011 in binary equals the number 11 in decimal. So we have to be able to go back and forth between decimal and binary because decimal is the number system we're used to using, and binary is the number system in which a digital system operates. So we have to be able to go back and forth between the two. And that's the purpose of this video, is to teach you how to do that. So now we'll do some more examples converting from binary to decimal. So the next example is that we have the number 10110011. Notice I have a subscript, base 2. So I know that's a binary number, and I'm going to convert that to a decimal number. So we're going to create the same place values table as before, but it's just going to be a little bit longer. Notice at the top of my table, I'm just going to rewrite the number 1 digit at a time. And then you're going to write the place values on the next row. Start from the right, work your way to the left. Your first place value will always be the base of your number. In this case, I have a base 2 number to the 0 power. And then you're just going to increase that exponent as you fill in your table. These are your place values. Now you just need to multiply each number on the top of your table by the place value below. So I'm going to be taking each place value, multiplying by either a 1 or a 0, depending on each digit in the number. And then we're going to add up these place values. 1 times 2 to the 7th is 128. That's 0. 1 times 2 to the 5th is 32. 1 times 2 to the 4th is 16. 0, 0. 1 times 2 to the first power is 2, and 1 times 2 to the 0 power is 1. Add all these up, and you get the number 179. That's your decimal equivalent for the binary number you started with. And that's how we would use the place values table in order to calculate the decimal value of any number. Now, I will say that it is helpful to memorize these powers of 2, at least up to 2 to the 7th, if not higher. If you already have it memorized that 2 to the 7th is 128, it just makes the math go faster at the end. So I do recommend that you memorize those values. So let's take a look at our next example. This time we have the number 01110110. We're going to convert it to a decimal number. Again, we're going to start with the place values table. The table is really just like a series of training wheels. As you get more comfortable with converting from one number system to the other, you won't need a table. You'll be able to look at this number and be able to figure out what powers of 2 you need to add together. But until you get to that point, always start with the table. And then you're going to just fill it in with your place values. Remember to start from the right, work your way to the left. You're always going to have an exponent that increases by 1 as you go. And the base of your number is going to be the number you use as a place value. So since I'm starting with a base 2 number, I'm going to have 2 to the 0, 2 to the 1st, 2 to the 2nd, etc. as my place values. Then you're just going to multiply each number on the top by the place value below. Simplify and add each one of these values together. So notice that for the last place on the left, I have a 0, so I'm not going to add that up. 2 to the 6th is 64. 2 to the 5th is 32. 2 to the 4th is 16. That's a 0. 2 squared is 4. 2 to the first power is 1, and that's a 0. So we can essentially ignore any column with a 0 and just add up the columns with 1s. And 118 is my base 10, or my decimal equivalent, for the number provided up here. Now I want you to try these out on your own. You can only learn so much by watching a video. You trying to learn anything from me from a YouTube video is the same thing as trying to learn how to swim by a YouTube video. You can't learn how to do it until you get in the water and try it yourself. So there are going to be several points throughout this video where I'm going to ask you to pause and try it on your own. That's your chance to see if you really get it. So I encourage you to take a second, hit pause, and try to convert the two numbers on the screen on your own. When you're ready, come back and I will show you the answers. All right, so for the number 1001111, you should have gotten 159. That's your decimal equivalent. For the number 110110, you should have gotten 54. If you didn't get these two answers, go look at your place values table, rewind this video a little bit, and make sure you set up your place values correctly. Then make sure that you have the right exponents and that you simplified properly. If you're still having trouble getting these answers, feel free to shoot me an email and we can talk about anything that might be going wrong. Now we're going to talk about going the other way, converting from decimal to binary. Let's say that I'm starting with a decimal number and I need to know how to represent it as a binary number. I'm going to use a process called repeated division by 2. We're going to write the remainders as we do this repeated division by 2. So again, we're going to go back to maybe 4th grade math and we're going to do some long division where we have to write a remainder. So to begin, we're going to take the number 18 and we're going to make a table. It looks like this. The divisor is always going to be the base you want to go to. I'm starting with a base 10 number and I want a binary number. Binary means base 2. So my divisor has to be 2 because that's the base I'm going towards. Then I'm going to take my number 18, I'm going to divide it by 2, and I'm going to write the result of that division in these two boxes here where I keep track of the integer part and the remainder for that division. So 18 divided by 2 would be 9 with no remainder. So I'm going to write 9, remainder 0. Then I'm going to take 9 and divide it by 2. 9 divided by 2 would be 4.5, which is the same thing as 4, remainder 1. I'm going to then take the 4, divide it by 2. That's going to give me 2, remainder 0. I'm going to take the 2 and divide it by 2, which is going to give me 1, remainder 0. Then I'm going to take 1 and divide it by 2, and I have 0 with 1 left over. That's the tricky part. 1 divided by 2, that's like technically a fraction, that's a half. So I don't have any whole number. I have 0 with 1 remainder. Now that I've done this, my binary number representing 18 is right here within the remainders from the bottom to the top. So if you write out these remainders from bottom to top, that's your equivalent for the number 18. So now you've just converted the number 18 from decimal to binary. This is the process that we can use when we want to convert this way. Now that you know how to go from binary to decimal, you can easily make a place values table to check your work. Make sure that 10010 really does give you 18. All right, next we're going to convert from decimal to binary the number 115. So we're going to make a chart. It's okay if you don't know how many rows you need. Just give yourself space. You're not going to know how many rows you need at the beginning. So give yourself a guess and add more if you need to. Next, we're going to take our divisor. It's going to be 2, and we're going to divide our number 115 by 2 and write the integer part as well as the remainder. So 115 divided by 2 is 57, remainder 1. And it's okay if you needed to grab a calculator to figure that out. Not a problem. Next, we're going to do 57 divided by 2. That's going to give you 28, remainder 1. Keep in mind any odd number that you divide is definitely going to have a remainder of 1. 28 divided by 2 is going to give you 14, remainder 0. 14 divided by 2 is going to give you 7, remainder 0. 7 divided by 2 is going to give you 3, remainder 1. Here's a little trick as well to make sure that you're doing this correctly. When you finish a row, if you do the first one, 2 times 3 plus 1, it should add right back up to what you started with. So keep that in mind as well. 2 times 3 plus 1 gives you 7. So you can use that to check your work if you need to. So let's continue. We have 3 divided by 2. 3 divided by 2 is technically 1.5, which is the same thing as 1, remainder 1. And then we have 1 divided by 2, which is 0, remainder 1. Keep in mind, you're dividing until you get down and the middle column is 0. When the middle column is 0, you're done. And now that the middle column is 0, we can stop, and our answer is right here within the remainders, bottom to top. So 1, 1, 1, 0, 0, 1, 1, bottom to top. That is our binary equivalent for the number 115. All right, now it's your turn. I want you to try to convert the number 76 into a binary number. Go ahead, take a second, hit pause, try it on your own, make sure you understand it, and then check back to see the answer. And here's what you should have gotten. 76 base 10 is 1001100 base 2. All right, now we're going to move on to another number system. So we know the decimal number system, that's the number system we use every day. And now we know about the binary number system. There are other number systems. Each number system just has a different base. So now we're going to go on to the hexadecimal number system, which we call hex for short. The hex number system has a base of 16. It contains digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it contains digits which are represented with letters. That's because I can't write the number 10 because the numbers 1 and 0 are already taken. 10 is not its own digit. 10 is a combination of digits 1 and 0. So we move on to letters to represent the next set of digits. So after 9, we have A, B, C, D, E, and F. Now the letter A represents the number 10. The letter B represents the number 11, and so on. So whenever you're in the hexadecimal number system, if you see a letter written within a number, like A9 or D5, those letters actually represent 10 through 15. So using this information, how might we convert the number 1F, base 16, to decimal? That's the question. Just like we did with binary numbers, we need to create a place values table. Here's my table. I have two digits, 1 and F. Since I have a base of 16, my place values are going to be based off of the number 16. And then I'm going to multiply each place value by the top row. So I'm going to have F times 16 to the 0 power and 1 times 16 to the first power. Just remember that F really represents the number 15. Remember, A equals 10, B equals 11, and so on. So if you continue that pattern, you'll see that F represents the number 15. So I'm going to have 15 times 16 to the 0 power, and then I'm going to have 1 times 16 to the first power for my place values. Simplify and add that up, and you'll get 31. So the number 1F in hex, which is base 16, is equal to the number 31 base 10. This is how we would use the hexadecimal number system. Here's another example where we're going to convert A2, which is base 16, to decimal. Here's my table. I'm going to fill in my place values first. Remember that 16 is because I have a base 16 number. And multiply each place value by our number above. Remember, A represents the number 10. Simplify and add these together, and you'll get 162. So A2 in hex is equal to 162 in decimal. Here's one more. We have a hexadecimal number with 3 digits now. 125 base 16. So remember, I'm not reading that as 125 because I'm not in a decimal number system. I'm in the hex number system. There is no hundredths place in the hex number system. So the number 125 in hex. Here's my place value chart. And now I'm just going to multiply each place value by the number above. Simplify and add them together. And you get 293. So I know the number 125 in hex is equal to the number 293 in decimal. All right, now it's your turn. Try to convert the number 50, which is base 16, 50, to decimal. And here's the answer. 50 in hex is 80 in decimal. Now that we know 3 number systems, we have to figure out how to go between all 3. So our next step is to go from binary to hex. And the nice thing about this is that hex is really shorthand for binary numbers. So for each group of 4 bits, you can write a hex digit. And that's all we have to do to go from binary to hex. So you're going to start from the right and work your way to the left, making groups of 4. There's a group of 4. There's a group of 4. and there's your group of 4. For each group of 4, you are going to write an equivalent hex digit. So for example, the number 0100 is the number 2 in hex. The number 0011 is the number 12. If you take this value right here, convert that to decimal, you'll get the number 12. In hex, we represent the number 12 with a C. So if you're looking at this and you're saying, how did this become 12? Look back at the place values. This place value is 2 to the 0, 2 to the first, 2 squared, 2 to the third. So I can ignore the first 2 because those are zeros. So I have 2 squared, which is 4, plus 2 to the third, which is 8. 8 plus 4 is 12. So make sure that you really understand going from binary to decimal before you try to do the other number systems. If you need to go back and look through the notes we did, go ahead and do that before continuing on. Make sure you understand that first. So for each group of 4 bits or 4 digits, you're going to figure out what that is in decimal, and then if it's a number bigger than 9, you're going to write it with a letter because we're going to hex. So if I started with the number 1101, 11000010, each group of 4 becomes a hex digit. 1101 becomes 13, which is a D. 1100 becomes 12, which is a C. 0010 becomes 2, which is 2 in hex. This is how we go from binary to hex. So if you look at the next example, 0101, that's equal to 2 to the 0 power plus 2 squared, because these are my two ones. Make the place value table and you'll see that. So you'll get 5. 1111, if you make a place value table and add up each one of these place values, you'll get 15. 15 is F in hex. So we write this as F5. Here's your turn to try this out. Remember, you're going to take each group of 4 digits, convert that to decimal, and if it's a number bigger than 9, write each digit as a hex digit. So try these out on your own and make sure you get it. And here are the solutions. We have 9A, 4D, and C06A. These are your hex equivalents for these binary numbers. Now we're going to go the opposite way. We just did binary to hex. Now we're going to do hex to binary. We can easily take any hex number and write it in binary by writing a 4-digit binary code for each hex digit. So now we're going the other way. We're going to take each hex digit. So here's a hex number, AF2. I'm going to take the 2 and write that out in exactly 4 digits, 4 binary digits. I'm going to take the letter F. I'm going to write that out in exactly 4 digits, 4 binary digits, and so forth. So here's how this will work. A is equal to 10. 10 is equal to 1010 in binary. So the letter A becomes a 1010. F is equal to 15. 15 is equal to 1111 in binary. So that's how I get 1111 for the digit F. And then 2 in hex is the same thing in decimal, it's 2. And in binary, 2 is a 0010. So each group of 4 comes directly from the hex digit you see there. And this is how we go from hex to binary. So with the next digit, we have 16 in hex. The 1 becomes a 0001. Remember, every hex digit we're going to write using 4, exactly 4 binary digits. And then the number 6 is 0110. It's okay if it's taking you some time to make a connection between the digit 6 and the 0110, for example. it takes practice, but over time, as we go throughout the semester, you will be able to look at any decimal number, like the number 8 or 4 or 2 or 6, and immediately know how that would be represented in binary. So it's okay if it's taking you a minute to make the connection between hex to binary or binary to hex, but with practice, you will be able to look at these and very quickly see what the answer is, because you'll be able to look at the number 2 and look at the number 7 and know exactly what that should be in binary as you practice. So the number 27 is 00100111, and then the number FA. F is 1111. F corresponds to 15. 15 is 1111. And then we have the digit A. A corresponds to 10, and 10 is the number 1010 in binary. So this is how we can go from hex to binary. Now let's talk about going from decimal to hex. Again, as we introduce a new number system, we're going to talk about how to go in between every number system that we've discussed. So we've gone hex to binary, binary to hex. Now we need to do decimal to hex. So just like when we did decimal to binary, we did repeated division by 2. Instead of repeated division by 2, we're going to do repeated division by 16, because if I have a base 10 number and I want to go to base 16, I just have to keep dividing it by 16 and writing down the remainders. That's one option. Or if dividing by 16 seems a little bit more intimidating than dividing by 2, you could convert the decimal number to binary first and then convert from binary to hex, because we just talked about how to convert from binary to hex. So it's your choice. Here's how you would do repeated division by 16. 516 divided by 16 gives you 32 with 4 left over. 32 divided by 16 gives you 2 with 0 left over. And then 2 divided by 16, again, that is going to give you a fraction, 2 over 16 or 1/8, which is going to give you 0, remainder 2. And my answer is 204. Again, right bottom to top. 516 base 10 is equal to 204 base 16. That's one way to do it if you want to divide by 16 repeatedly and figure out the remainder. Your second option is to convert 516 to a binary number. So you can just keep repeating by 2. Now you have a binary number if you go from bottom to top. There's your binary number. Now go from binary to hex. Start from the right. Make groups of 4. And notice that your last group doesn't have 4 bits. That's okay. Just put 2 extra zeros in front to make it 4. So there's my groups of 4 color-coded. This represents the number 4. This represents the number 0. And this right here, if I put 2 extra zeros in front, I have the number 0010, which is the number 2. So I still get the same answer, 204 base 16. So it's your turn. Try to convert the number 84 to hex. You can divide by 16, and then your answer will be in the remainders, or you can do repeated division by 2, and then convert that to hex. It's your choice. Do what you feel comfortable with, but see if you can get the answer on your own. If you decided to do repeated division by 16, here's what your table would look like. 84 base 10 is equal to 54 base 16. If you decided to do repeated division by 2 and then convert it, you still should have ended up with a final answer of 54 base 16. Now we're going to talk about yet another number system, the octal number system. And by now, I'm hoping that you're comfortable with the idea that you can pretty much go into any number system you choose. It's just a matter of manipulating the base. So what I want you to do is think about the hex, decimal, and binary number systems and what we've done so far and extend it. I want you to try to answer all of these questions on the screen by yourself first. If you can answer all of these questions on the screen, then you totally understand number systems. And think about how we applied the base of each number system to all of the examples before. If I now give you the octal number system, where we have a base of 8 instead of a base of 2 or a base of 10 or a base of 16, think about what might change in how we convert to decimal, or convert from octal to decimal, or decimal to octal. Think about what might change in our calculations or in our place value tables or in our division tables, and see if you can apply the concept on your own to these questions. So take a pause. This is sort of like a self-check. If you can figure out these answers, then you're on the right track for understanding number systems. So when you're ready, come back and the solutions will be on the screen. So first, the octal number system has a base of 8. If it has a base of 8, that means it has 8 digits, starting with 0 and going up to 7. Remember, the 8 means the number of digits, not what the digits goes up to. So the octal number system has digits 0 through 7. If you're going to convert the following octal numbers to decimal, you're going to need to set up a place values table. The last row of your place values table would look like this. You would have 2 times 8 to the second power, plus 0 times 8 to the first power, plus 5 times 8 to the 0 power. Notice that I have my place values set up with 8. And then I have just basically 8 to the 0, 8 to the first, 8 to the second, etc. So that number comes directly from the fact that this is a base 8 system. Add it up and you'll get 133. For the second number, 17 in octal comes out to be 15, base 10. And then if you're going to convert decimal to octal, you have to use repeated division by 8, because I want to go to octal, I want to go to base 8, so I have to divide by 8 and keep track of the remainders. And here's what you should have got if you did repeated division by 8 on the number 80 and the number 240. So again, this is more of a self-check. Now that we've talked about the octal number system, you should feel pretty comfortable being able to tackle any number system. I could give you base 12, base 3, base 7, base 4. The rules stay the same. We just change the base and apply it accordingly. That's the whole concept behind number systems. It's just understanding how to go from one system to another system. So another system that is used often in digital systems is the binary coded decimal system, or BCD. It's a method of representing decimal numbers by writing each decimal digit using a 4-digit binary code. This is the exact same thing we do with hex. When we have a hex number, we take each digit and represent it with a 4-digit code. We're doing the exact same thing here, except instead of starting out with a hex number, I'm starting out with a decimal number. That just means I'm only going to have digits 0 through 9 to represent. I won't have the letters A, B, C, D, E, or F in my decimal number. But other than that, it's the same idea. So if I take the number 19, I know that the number 1 is 0001. The number 9 is 1001. Put them together, that's a BCD number. So BCD takes a decimal number and represents each digit as a group of 4 bits. The number 157 or 157 base 10, take the number 1, write it as a 4-digit code. Take the number 5 and write it as a 4-digit code. Take the number 7 and put them all together. And for the last one, 4, 5, 6, 7, you're just, again, going to write out each one of those as a 4-digit code. That's the BCD system. BCD is used very frequently when we want to actually display a decimal digit on a piece of hardware, like an LCD display or a watch display or a screen. We use BCD a lot when we want to display the number 9, the number 4, the number 2. We send a BCD code to a particular circuit that can display that actual number. We'll learn more about BCD and how it is used throughout the semester. Here's your chance to try these out, but we have a BCD number that we're going to write in decimal. Try these out and see if you can go the other way. So you have a BCD number. What's the decimal equivalent? Remember, all you're going to do is take each 4-digit code and convert that to a decimal number. So the number 1001 is 9. The number 0010 is 2, so that represents the number 92. Now, be aware that the subscript here tells me this is a BCD number and not a strictly binary number. So I'm not going to use place values to figure out what this represents. If you use a place value table on this number, you're not going to get 92. So subscripts matter. They're very important. The fact that this subscript is BCD tells me I only need to break this down 4 digits at a time. If this had a 2 instead of BCD, that tells me I have to use a place values table to figure out what this number is because it's a binary number. So binary and BCD are 2 different systems. You have to keep that in mind when you're looking at various number systems. So the next one, this group here is a 5. 0101 is 5. 1001 is 9. 0111 is 7. 0011 is 3. And then the last one is 2295. So that's another number system that we'll encounter as we go throughout the semester is the BCD number system. Okay, so we've talked about several number systems today, and here's a small chart that starts to put some of these number systems together. We talked about the decimal number system. We talked about how to represent numbers in binary, in hex, and then in BCD. So now you can see the differences. So for example, the number 10 is 1010 in binary, it's A in hex, and it's 0001 0000 in BCD. Remember, binary and BCD are 2 totally different systems, and this chart should definitely be able to display that. Look at the differences between binary and BCD. So remember to use your subscripts whenever you're thinking about converting a number from one system to another. It is my strong recommendation that you try to memorize as much of this chart as possible. Like I said, it gets easier when you can think of the number 12 and immediately know that 12 is 1100 in binary. The more that these numbers are at your fingertips, the easier it is to understand the circuits that we're going to design and build throughout the semester. So start trying to memorize some of these values because it'll make everything easier if these are at the tip of your fingers. A couple of other terms that we'll use when referring to binary numbers. 1 digit is called a bit. You've heard me say that a few times. A single digit is called a bit. So a 0 or a 1 is called a bit. When we look at a string of bits written out, the number on the far left is your most significant bit, MSB, most significant bit. The number on the far right is your least significant bit. A group of 4 bits is called a nibble. A group of 8 bits is called a byte. That's 8 bits. And then a group of 16 bits is called a word. So a couple of different terms we'll use when referring to bits or groups of bits. And the last thing we're going to talk about is another system called ASCII. There are times when a computer should recognize codes that represent letters of the alphabet. So for an example, whenever you type on your keyboard, there's a button with a picture of a letter on that button. Maybe you want to type the letter A or the number 3 or the pound sign. How does your computer know to display a picture of the letter A when you hit the button A? The ASCII code is how we accomplish that. So these are alphanumeric codes, the ASCII code, which represents all of the letters you find on your common keyboard. So the letter C, the letter F, the uppercase letter C, the lowercase letter F, a semicolon, the @ symbol. All of those are represented by a code. And all of these codes represent what we call the ASCII code. And so what happens is, let's say that I want to display the letter B on my computer. When you type the letter B on your keyboard, there's a corresponding code that is sent to the microprocessor of your computer. That code tells your computer to display an image of the letter B. That's the ASCII code and how it works. So the ASCII code is a 7-bit code that represents the digits or the letters that we want to show on the screen. So here's a snapshot of some of the ASCII codes for some of the things that we may use to type on a screen. So if I want to type the letter F, the corresponding code that my computer and my microprocessor is going to use to figure out that I want to display that letter is right here in this table. And notice that it's written in hex and decimal. So the hex value is here. The decimal value is right next to it. So if I want to send a code for the letter F and I want it to be lowercase, I need to send a 66 in hex, which would be 01100110. That's 66. So I'd have to send that code in order to display the image of the letter F on my screen when I hit the button F on my keyboard. That's what the ASCII code helps us to do. And we're going to tie in the ASCII code to an example about parity. So parity is an error detection method. And whenever we have digital systems, we have systems that send a signal and we have systems that receive a signal. For example, if you've ever tried to print something from your computer and you've hit print and nothing ever came out. When you hit print, you sent a signal to the printer and that message was somehow not received or corrupted because whatever you were trying to print never came. So if that's ever happened to you, that's an example of a system where you have a transmitter and a receiver, and sometimes there's an error in the message that is sent. Parity is a simple method to detect an error so that you can be aware of it as the user of a system and maybe be able to do something about it. The idea behind parity is that you take a piece of data. Say I'm going to send a message to my printer just to print something. If I'm going to do that, I'm going to send a long message full of zeros and ones that tell my printer what I want to print. The parity bit is something that would be added to the beginning of the message, and it would be a 0 or a 1, depending on the number of ones in the message already. So just as an example, let's say I'm going to send the ASCII code for the letter A. If I go back to this table and look at the letter A is 4, 1. In hex. Here's my 1. Here's my 4. There's 7 bits. And then I'm going to add a parity bit to the beginning of the message. And that bit is going to be chosen depending on whether you're using even parity or odd parity. If you're using even parity, that means the total number of ones in the group, including your extra bit, must be an even number. So here's an example. Let's say I'm going to send the code 1001000. That represents, in hex, that represents 48. If I go back to my table, that means I'm trying to send the letter H, a capital H. That's the message I want to send. If I'm using even parity, I'm going to add another bit to the front of the message. I have to add a bit. It's going to be 0 or 1. I'm going to pick it to be 0 because there is already an even number of ones in the message. That's the idea of parity and adding a parity bit. So my parity bit would be a 0 so that my entire message, including what I added, has an even number of ones. If I was going to send the message 0111000, this time my parity bit would be a 1. Because I already have 3 ones, so I need to add 1 more to make it 4. This is my total message that would be sent. If you're using odd parity, it's the same thing except your entire code group needs to have an odd number of ones, including the parity bit. So if I'm going to send the same message as before, but now I'm using odd parity, my first message would get a 1 added to the front so that I have 1, 2, 3 ones in the message. And if I was going to send the same message as before, the 0, 1, 1, 1, 0, 0, 0, it already has an odd number of ones, so my parity bit would have to be 0 so that it stays an odd number of ones. That's the idea of parity. So how do we tie this all together? Let's say that your computer and your printer have to communicate. Let's say that they communicate using even parity. If the computer sends a message to the printer is going to have a circuit within it to determine how many ones are in the message, an even number or an odd number. If the printer gets a message with an odd number of ones, and it knows it's supposed to be an even number of ones, the printer can display an error message and say, there's something wrong. And then as the user of the computer, you know that the data you sent was not received or that something was corrupted within your message. That's the purpose behind parity. So later in the semester, we're going to design a circuit that will generate your parity bit for you. It will also check the parity of a message and determine whether there's an error. And that's where this example is where those circuits are derived from. So again, parity is an error detection method which will help you to determine if a message has been corrupted, basically by counting the number of bits in a message. And you would have a predetermined system. So when you design the computer and the printer to work together, you would predetermine, oh, it's going to be even parity, or oh, it's going to use odd parity. So that as these two systems communicate, both know what system they're communicating within. So assume that a computer and a printer are designed to use even parity. The computer sends the following message to the printer. If we count the number of ones in the message, we see there are 1, 2, 3, 4 ones. That's the message that was sent, even parity, even number of ones. Let's say that the printer receives the message. The printer would determine if the data received might contain an error by looking at the number of ones and expecting it to be an even number. So, now let's put parity and ASCII together. The question is, what bit strings, or what bits, would a computer transmit to send the message hello using ASCII with even parity? So if I wanted to send this message, I'd have to send one letter at a time using a code for each letter, and I have to attach even parity to the message. The letter H is represented in hex. That's 4, 8. If you write that in decimal, there's your 4, there's your 8. Attach a parity bit in front, there's your message. If I were to send the letter E for hello, that's 45 in hex. Write the 4 as 0100 and the 5 as 0101 and count the number of bits. I have 1, 2, 3 bits. I'm using even parity, so I need an even number of bits. I'm going to make that bit a 1 so that they're even. Here's the letter L. Its code is 4C in hex. So we're going to write that out in binary. C is 12. 12 is 1100. That's where that comes from. Count the number of bits. 1, 2, 3. So L has to have a fourth parity bit of 1 to make it an even number of bits. And then O, which is at the bottom, is 4F. So if I were to take the ASCII codes in order to send a message, maybe I'm typing the word hello from my computer to my screen, the parity bit would be chosen using even parity. And again, even parity or odd parity, that's all up to the person designing the system at the time it's created. But this is what those messages might look like. And as I'm sending these messages from one system to another, both systems would be equipped to determine if there is an error based on the number of ones in the message. That's the idea of parity. So if you think about parity, It's nice and easy, but because it's nice and easy, there are two very, very big downfalls with the parity method. That's why it's very simple, and it's a very introductory way to monitor a system and to monitor the integrity of the data being sent between two systems. So there are two downfalls. The first one is the parity method can't tell you which bit is wrong. It just tells you something is wrong, which may not be very helpful if you're trying to diagnose a problem. So let's assume you have even parity. Here's the message that was sent. 11010001. There's 1, 2, 3, 4 bits. But the number 100100001 is received. There's only 3 ones. So because this is a system with even parity, you'll get an error message, but you have no idea which bit is wrong. And how would you go about figuring that out? So it's not very helpful in helping you to diagnose the issue. It just tells you that it exists. The other issue is that the parity method won't detect an error if 2 bits are incorrect. So let's assume we have odd parity. Here's the message that was sent. Notice I have 1001, 0010, and I have 3 ones. But look at the message that was received. That 0 became a 1, that 1 became a 0. There's 5 bits in the message. That's an odd number, and an error won't be detected. So the parity method is great for simple error detection, but it definitely has some downfalls, and those are 2 of them. So this lecture pretty much encompassed number systems and parity. Going forward, start practicing going from decimal to binary and back again. We will use this all of the time. It is the language that we speak in any computer programming course. The number one foundational thing you have to know is the binary number system, and then the corresponding number systems like hex and BCD and so forth. Start practicing now. As we go throughout the semester, you have to be able to convert easily between these systems because it's an essential tool for this course. So with that, that's the end of this video. If you have questions or concerns, please shoot me an email and I will do my best to help you out.